To start off with, we're going to look at what's called the basic counting principle. And it is called basic because it is a very basic idea. If we've got a number of events and we know it can happen in m different ways, and then subsequently there's another set of events that can happen in n different ways, then the number of ways the two events can happen, m times n. Now, why is this useful? It really comes down to probability questions. You remember when you're drawing tree diagrams and what have you? Well, this is just to save time. We don't really need the tree diagram. What we need to know is how many branches it has. So if I know I'm going to start off and the first event branches off m ways, then the second event will branch off n ways, I know I'm going to end up with m times n branches or possible outcomes all up. And this whole idea of this topic of permutations and combinations is to work out the number of ways things can occur. And it simplifies then probability problems because they don't need to draw tree diagrams and what have you. So 3 dice are rolled. How many ways, how many different possibilities have we got? Well, the first dice can roll 6 different ways. The second, 6 different ways. The third, 6 different ways. So all up, there are 216 possible outcomes. Okay, well how many of those will they show the same number? So go, okay, I'll roll my first dice. There are 6 different things that could happen. But now I want the other ones to show the same number. So roll the second one, there's really only one thing that I want, it to be the same number. And then I roll the third one, and again there's only one thing that I want to be the same number. So there are 6 different ways they could all show the same number. Now, logically that makes sense. They could all show a 1, all show a 2, all show a 3, and so on. So if I then ask the next logical question, what's the probability? I'm going to roll 3 dice. What's the probability that all 3 dice show the same number? Well, it's got to be 6 out of 216. The total number of outcomes that I'm looking for, there were 6 possible ways of happening over total number that could possibly happen. And we said there were 216 different ways things could possibly happen. So I've managed to get that probability without having to draw up a sample space. I can just bang, there's the answer. 6 over 216 simplifies down to 1 in 36 chance. So that's what we call the basic counting principle. Here's an HSC question from 1996, which also uses that same sort of idea. So we've got mice, we're putting them in the centre of a maze. The maze has got 5 exits. Each mouse is equally likely to lead through any of those exits. Thus, the probability of a given mouse going through a given exit is 1 in 5. There are 4 mice, A, B, C and D. They're put in the maze and they behave independently. What's the probability that A, B, C and D all come out the same exit? Okay, so I'll look at each mouse independently. The first mouse has a probability of 1. Okay? It's just going to leave. It has 5 choices out of a possible 5 choices. 5 on 5 is 1. The next mouse, though, has a probability of 1 in 5. Yes, there are 5 choices, that goes on the bottom of the fraction, but on the top of the fraction, total number of ways it can leave, well, we want it to go through the same door. So it's got a 1 in 5 chance. And then so does the third mouse, and so does the fourth mouse. So all up, there's a 1 in 125 chance that they all go through the same door. So the probability that A, B and C go out the same exit, D goes out a different one. So I can start again. Okay, let's roll the mouse. Okay, so D, I'm going to look after D first. So D goes along, can go out of any exit, probability of 1 that it goes through. The next mouse comes along, its restriction is it can't go through the same one as D. So it's got 4 choices out of 5. So the next mouse comes along, 4 out of 5. Now the next one comes along, well, it wants to go through the same one as that second mouse. So it now has a chance of 1 in 5 of that happening. And then the last mouse also a 1 in 5 happening. Total probability of 4 in 125. So, What is the probability that any 3 of the 4 mice go out the same exit and the other mouse goes out a different one? Well, we just worked out the probability that D uses a different exit and the other 3 go through the same. Okay? But D was just a mouse. Here we're now saying any of them. So probability that A uses a different exit, if I wanted to work that problem out, that would also be 4 in 125. Probability that B uses a different exit, that would also be 4 in 125. Probability that C uses a different exit, that would also be 4 in 125. So therefore, the probability that any mouse uses a different exit to the other 3, and those 3 go out the same exit, must be 4 lots of 4 in 125, 16 in 125. And then the last part of the question, I think this was the last part of it. What then is the probability that no more than 2 mice go out the same exit? No more than 2 mice go out the same exit. Well, let's think what we've worked out so far. In the first part, we worked out all 4 go through the same exit. The second part, or actually the third part, we worked out that 3 go through the same exit, 1 goes through another one. Our question is now saying no more than 2. Okay. No more than 2. Basic idea in probability is using complementary events. Sometimes it's easier to work out the other situation than the one you're looking for. And we know all probabilities must add up to be 1. So I can say it's 1 minus the other possibilities. The other possibilities in this question are the 2 things we have already worked out. No more than 2. So then the other possibility is more than 2 go through the same exit. Well, that means 3 go through the same exit, which we've worked out. 4 go through the same exit, which we've worked out. So all I've got to do for this question is subtract the 2 answers we've already worked out from 1. And that gives us 118, 125. Really interested in is permutations, a specific type of situation. What a permutation is an ordered set of objects. The actual order that things happen is important. Okay? So we're going to look at a few different cases here. The first case is I've got n different objects and I'm going to use all of them. So I'm going to order a set of n objects from a set of n. So all of the objects are going to get used. I'm going to order them all. Imagine they're in the corner. We've got n different objects over there. How many ways can we line them up? So I'll just grab them and I'll line them up out the front. So I go over to the corner and I want to get the first object. Basic counting idea. How many ways could I get that first object? N. Right, there are n different things I could choose for the first object. So first object n. Right, great. I've grabbed it. I've put it there. I'm now going to go get the second object. How many ways could I now get the second object? N minus 1. I'm now going to go get the next object. How many ways?
N minus 2.
And so on and so on and so on. But because I'm using all of them, there'll come a situation where eventually I'll go there and there's only one object that I could grab. And so we'd keep going down, multiply by 1. Now, you've seen that before somewhere. N times n minus 1 times n minus 2 times dot, 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 down to 1.
Seriously?
Yeah, do you remember what it was? N factorial. That's it, n factorial. So I don't have to go n times n minus 1 times n minus 2. If I want to arrange 5 objects, I'm going to use them all 5 factorial ways. I want to arrange 6 objects, 6 factorial. 7 objects, 7 factorial, and so on and so on. Okay? So, as an example, I've got 5 boys and 4 girls. I'm going to arrange them in a line out the front here. How many ways? No restrictions. That's a very common question to ask, because no restrictions basically is, if we're going to create a probability question, that would be the bottom of the fraction. Total number of possibilities, if anything could happen. And that'd be the bottom of the fraction. So no restrictions. Well, if there's no restrictions, it doesn't matter that there's 5 boys and 4 girls. This is 9 people over there I'm going to grab. I want to put 9 people in a line, 9 factorial ways of doing it. Okay, no restrictions, 9, gender, does not matter. That'll end up being the bottom of our fraction for any probability question. So 362,880, a heck of a lot of ways. That's just arranging 9 people. Now you can see why often when people get you to line up, they say, can you line up in alphabetical order? Makes life a lot easier because there's only one way of doing that. Okay. But what if we now said, no, what I want is, look, okay, we're going to do a random arrangement here, but what's the chance? You just randomly stand up the front. What's the chance that the boys and the girls alternate? All right. Well, here's how I do it. Whenever you're looking at these, the restriction is what is important. You look after that first. If the boys and girls alternate, what is the restriction here? Yeah, boys got to be first. Because I've got more boys than I have girls. So if I start with a girl, I'm going to run out of girls. So I'm going to start with the boys. I'm going to arrange them first. So the first person must be a boy. There's only one way that can happen. It's a boy. Okay. Now I've decided I'm going to arrange the boys. How many ways can I arrange the boys?
5.
5 factorial. There's 5 of them. All right. Now I'm going to arrange the girls. But what I'm going to do is I'm going to say, look, you arrange yourself. But when you go and stand in the line, just make sure there's a boy in between. So they'll just slot in between the girls and then they'll alternate. So there's 4 factorial ways of arranging the girls. So total number of ways of them alternating, 2,880. 2,880. So if we were to ask that probability question, probability of the boys and girls alternating, we now know, 2,880 out of 362,880, a 1 in 126 chance of that happening. But hang on, sometimes people rock the boat. 2 of the girls wish to be together, probably want to talk. Happens a lot. So okay, we're going to look after that restriction first. So really, when the 2 girls say they want to be together, it's like saying, how many ways can I arrange these 2 girls? It was 2. A bit like that, well, they can be like that. So 2 factorial. Okay, we've organised them. I haven't put them in the line yet, but they now become like one object. One object. Because now I'm going to say, well, I'm going to arrange 8 objects. The 7 people who it didn't matter, and this little group of 2 that really have got to stay in that set order, so they may as well just be one person. So all up, I have 8 objects I'm arranging, 8 factorial. So 2 factorial, 8 factorial, 80,640. So you always look after the condition first. I arrange them. I haven't put them in the line yet. They're just an object now. We've worked out how that little group's going to work. And then we say, right, how many objects now do I have to arrange? Well, what if we don't use all the objects? So I've got n objects. I'm only going to use k of them. K is less than n. I'll go over there and I'll say, all right, I'm going to get the first one. How many ways can I get that first object? N. There's still n objects over there. That has not changed. So I'm only going to use some of them. So I've got n objects. I'm going to go get the second object. How many ways? n minus 1. That hasn't changed. I'm going to go get the third object. How many ways? Has not changed. But then at some point, I'm going to go and get the kth object. How many ways can I arrange the kth object? There's a clue. Have a look at what we've already written down. The first object, there was n ways. 2 objects, there was n minus 1 way. Third object, there was n minus 2 ways. K objects, n minus k plus 1. Well, that's a bit confusing, so I make it look even more confusing, and it makes it easier. Exactly right. It's times 1. Because the top of the fraction is the same as the bottom fraction. So all I've done is times by 1. But have a look at the actual numbers themselves. If I had kept going, so we got n minus k plus 1, the next one would have been n minus k. Then the next one would have been n minus k minus 1, and we would have kept going to 1. So I could rewrite this to say, hang on a sec, that's just n factorial on the top of the fraction. And it's n minus k factorial on the bottom of the fraction. And what we're actually doing is we're dividing by the number of ways we could arrange the things we didn't use. Because we don't care about them. We didn't use them. So their arrangement doesn't matter. And so that's what we've really done here. I used k objects, so there was n minus k objects that I did not use. So the number of ways I could arrange all of them, but I divide it by the number of ways I could arrange the objects that I did not use. N minus k objects. There is a button on your calculator to make life even easier. It's the permutation button. On some calculators, I think it's on the division symbol. You press shift or inverse or second function, and you might find it there. But it does make life a little bit easier. But if you haven't got it, no big deal. You can use n factorial on n minus k. It still is important that you know where it came from, because sometimes you might get a question that's theoretical. It might not have numbers. It might have algebra, so you got to, So let's have a look at this one. Letters of the word problems. We want to know 5-letter words. So we're not going to use all the letters. 5-letter words. And there's no restrictions. And no restrictions means this is maths. It's not English. So as far as I'm concerned, blems is a word. Smleb is a word. Robble is a word. Any arrangement of 5 letters is a word. Okay. So number of restrictions. Well, 8p5. There are 8 letters there. I'm only going to use 5 of them. So that's 8 factorial on 3 factorial for those that are using the factorial buttons. But the answer you should get is 6,720. Let's make it more interesting. The word has to begin with a P. So we look after the restrictions first. How many ways can the word begin with the letter P? 1. It begins with P. There's only one way it can happen. So the first thing, I've placed the P in the word. You're going at the front. Only one way I can do it. We now need another 4 letters from the remaining 7. So the question now becomes, how many 4-letter words from Robblums? I've used the P, it's gone. So it will now be 7p4. 7 remaining letters, I'm only going to use 4 of them. 1 times 7p4, 840. Let's make it even more fun. This time, P is included. Doesn't have to be at the front. It's just going to be in the word somewhere. But not at the beginning this time. And M, we don't like the letter M. We're not going to use it. How many ways can we do it? Okay, look after the restrictions first. P is included, but not at the beginning. How many ways can I place that letter P? 4. Not at the beginning. So I can't take the first spot. All right, P is now being placed in the word. We now have to get the rest of the word. We're not allowed to use the letter M. So there are 6 letters left, Robbles, and we want 4 of them. So 6p4 ends up being 1440. Let's try this one. 6 people in a boat. The boat's got 8 seats. 4, spelled really well, on each side. What's the probability that Bill and Ted are on the left side of the boat and Greg is on the right side of the boat? So it's a probability question. So for the bottom of the fraction, I'm going to want to work out total number of possibilities with no restrictions. So I'll do that first. If there's no restrictions, there are 8 seats. I'm going to use 6 of them. How many arrangements? 8p6. So 20,160 ways these people could go in the boat. Now let's look after the restrictions. Bill and Ted have come along and said, hey, we got to be on the left side. There's only 4 seats on the left-hand side that they can select from. Going to use 2 of them. So 4p2. But now Greg goes along and said, well, if they're on the left side, I want to be on the right side. There are 4 seats on the right side, going to use 1 of them. So 4p1. The other people, so the other 3 people are just shaking their heads going, can't believe that. What's the matter where you sit? So now they're going to come along. How many seats are left? Well, they've used up 3 of them. 5 seats left. we're going to use another 3 of them, 5p3. Gives us a grand total of 2,880. So thus our probability, Bill and Ted are on the left, Greg's on the right, 2,880 over 20,160 tidies up to be just 1 in 7 chance. 1 in 7 chance. All right, let's look at an HSC one. 5 coloured blocks, a red one, a blue one, a green one, a yellow one and a white one. She stacks blocks to make a tower. But notice, a block of 1 is not a tower. It's just a block. So until you stack 2 blocks, you get a tower. So you can have 2, 3, 4, 5. How many different towers that are 3 blocks high? Oh well, she's got 5 blocks to choose from. Because they're different colours, then the way they're arranged is important because you'll get different towers. So from the 5 blocks, going to use 3 of them, 5p3. So it's 60 different towers. Well, how many towers in total? Okay, we said a block of 1 is not a tower, it's just a block. So if I use 2 blocks, 5p2. That works out to be 20. 3 blocks we just did, that's 60. 4 blocks, 5p4. 120 ways of doing that. And then of course use all the blocks, 5p5, also 120. So in total, 320 different blocks. Different blocks? 320 different towers that could be made. All right.